Good evening, all. Welcome to the inauguration ceremony of the National Webinar Series organized by the Department of Electronics and Communication Engineering, University College of Engineering, Muttam. Let's begin the program with a silent prayer. Thank you. Now, I would like to invite Mrs. Ashalata PT, Head of the Department of Electronics and Communication Engineering, for the welcome speech.
A very good evening to everyone present here. It's our proud privilege that today our guest is the past director, Dr. P.K. Padmakumar sir, as our chief guest. He was the former MG University syndicate member. I extend a warm and cordial welcomes to sir. With the warm greetings, it gives me a great pleasure to extend a warm welcome on behalf of the Department of Electronics and Communication Engineering, conducting a wonder webinar on chip design in the electronic system design and manufacturing ecosystem by Mr. Robin Davis, Executive Account Manager, Synopsys. He served many companies like former director in Wipro Japan and former vice president in Black Pepper Technologies, and he is also a UCE alumnus. I welcome you, sir. I also welcome our beloved principal, Dr. V.G. Gidama Miss, for her continuous support and encouragement to conducting this webinar. We welcome you, Miss. I also welcome all the HODs, teaching and non-teaching staffs of today's session. I also welcome the today's session all the semester students for registered, and I welcome all students in today's webinar and thank you for registering. Once again, welcomes you all for this wonderful session webinar on chip design in the electronic system design and manufacturing ecosystem. Thank you.
Thank you, ma'am. Now, let me invite our respected principal, Dr. Geedama VG, for the presidential address.
Honorable Director, Dr. Padmakumar sir, esteemed Speaker, Mr. Robin Davis, respected Vice Principal, Dr. Josebasan sir, our Administrative Officer, Shivprasad Karta sir, our favorite HOD, Ashalata Miss, coordinators of the webinar, Deepu sir and Anish sir, other HODs, teachers, non-teaching staff, participants, and my dear students, good evening to all. At first, I thank Padmakumar sir for inaugurating this function. I know he is always very busy with his meetings and discussions, but whenever we invite him for any function, he will make sure that he will attend the meeting. He accepts our invitation without any reluctance. And normally, he will be online at exact time. Thank you very much, sir. Thank you so much, sir, for your continued support and cooperation. Now, this is the third webinar of our college during the lockdown period. Earlier, many years ago, in our college, each department was having its own departmental associations, like Department of Electronics and Communication Engineering, Department of Computer Science and Engineering, etc. And the association secretary was elected through the college union election. And the designation of the association secretary was very important and glamorous at that time, because he or she was responsible for the entire technical events of the department. And the department also, it was a prestigious issue for the department. And they will conduct a series of technical events in the department, like seminars, symposiums, exhibitions, quizzes, etc. Because they realized that students and staff exposed to these sort of activities means they are getting knowledge. They are getting, they understand the recent trends and modern technologies in the area. And we know that if we get knowledge, that means it gives us confidence to do things, confidence for innovation, and it gives us courage to accept challenges. But later, 1 year, the college stopped electing association secretary to the college union election, and that was the end of the association activities. But then TechFest came into action. But the problem was that the TechFest didn't give enough attention to the technical events. Rather, it was a sort of celebration. Anyway, last year, I am happy to say that in last year, a few of our departments have restarted the association activities. I am really glad that one of the departments, it was Department of Electronics and Communication Engineering. And today they are organizing another event, technical event, this webinar. I am glad that all the staff, HOD and all the staff are with this. I congratulate HOD, Ashalada Miss, the coordinators, Anish sir, Deepu sir, and the students, and all the teaching and non-teaching staff of the department for their efforts, for their teamwork and team spirit. Anyway, last year, the reopening of the association activities, I couldn't attend that function, but my best wishes are always with them. And I am also glad that today's esteemed speaker, Mr. Robin Davis, he is an alumnus of our college. Last year, he uploaded a short film, a promotional video film about our college. We strongly believe that this sort of activities helped us improving the admission last year. In that short video film, he was talking about the skills and capabilities he has acquired from our college. And he has also mentioned about the various activities he involved at that time, like career guidance and placement, IEEE, then college magazine, etc. And he also mentioned that he got a number of jobs, and finally, I understand that he attained the position of director global Wipro Japan. And it's a very high position, and later on he moved to another job. Anyway, we are proud of you, and today he has offered another free service to our college. He has offered to deliver the keynote speech today in today's webinar. So we are really thankful to you for all your service, and we are really proud of you. The department and the college, we are proud of you. And I also wish that today's speech, it will enlighten the staff and students, and it will be beneficial for all the participants. I wish you all the participants a very active and fruitful webinar ahead. With these few words, I wind up, and thank you. Thank you all.
Thank you, ma'am. Now it's time for the inauguration. Dr. P.K. Padmakumar, former Honorable Syndicate Member of Mahatma Gandhi University, is currently the Director of Center for Professional and Advanced Studies. He has also served as Associate Professor in the Department of Botany at NSS Hindu College, Changanasheri. I request our guest of honor, Dr. P.K. Padmakumar, for the inaugural address. Over to you, sir.
I think sir couldn't join us. I request our Principal Madam to inaugurate the session.
I don't know what happened to him today. Normally, he always, as I have already mentioned, he always make it sure that he will attend the meeting without any fault. And by maybe today something else has happened. So
Yes.
today I have got dual responsibility. I am glad to inaugurate this webinar. I declare that this webinar is inaugurated. Thank you.
Thank you, ma'am. It is a great honor for me to introduce and welcome our chief guest this evening, Mr. Robin Davis. In a career spanning over a decade, Mr. Robin has been involved in microcontroller VLSI design, solution building, and business strategy roles in both product and service organizations in India and Japan. He started his career as a DFT engineer for ISO 26262 compliant automotive grade application specific integrated circuits. He later moved into VLSI solution architect and various business management roles to manage large international clients in industry verticals such as manufacturing and high-tech, automotive, medical and wellness, IoT and consumer, industrial, defense, in technology areas such as VLSI, embedded systems, artificial intelligence, machine learning and deep learning, enterprise and cloud computing, mobility, telecom technologies, wireless technologies, automotive safety integrity level, and advanced driver assistance systems. Mr. Robin went on to achieve several accolades during his career, including C-Suite awards, and served as director, product engineering group at Wipro in Yokohama, Japan, before he took up the role of director and vice president roles in global strategy at various technology companies. Mr. Robin is currently a part of the executive account management team at Synopsys. At Synopsys, he is responsible for revenue sustainability and growth across several multinational accounts and is a member of the Synopsys User Group Core Committee. Outside of work, Mr. Robin is a martial arts enthusiast who holds a second Dan black belt in Jojo Karate and has co-founded a martial arts trust which aims to equip youngsters and adults with self-defense techniques. Today, we are privileged to have an opportunity to listen to him this evening. On behalf of all gathered here, I welcome you, sir, for the keynote address.
Thank you. Deepu, am I audible?
Yes, sir, sure.
All right. നമസ്കാരം. എൻ്റെ പൂർവ്വ വിദ്യാലയത്തിൻ്റെ ക്ഷണം സ്വീകരിച്ച് ഈ വെബിനാർ സീരീസിൽ പങ്കെടുക്കുവാൻ സാധിച്ചതിൽ ഞാൻ കൃതാർത്ഥനാണ്. One of the greatest things about India is the tremendous amount of passion for education and for learning in general. This is a great legacy that all of us should certainly leverage. We all know that the human mind is tremendous, of enormous amounts of potential, or is capable of enormous amounts of potential and can achieve anything that it truly wants. So I think the secret to a successful future really is to discover what it is that you truly want and what you are really passionate about. It is important that in the process of living our lives, we find what truly inspires us and what makes us wake up every morning and just get to it without anyone even having to pay us for it. That one thing is the fire that will drive you forward. That one thing is what is going to make your dreams come true. And that one thing is what is going to essentially help you build your dreams in the first place. Now, that one thing doesn't even necessarily have to be in the field of engineering. People do well in all walks of life. One thing is for sure, each of one is truly passionate about something. And all you need to discover is what it is that you are truly passionate about. The funny thing is that once you do that, every hurdle in front of you presents itself as an opportunity to solve a problem, to make someone's life better, and most importantly, to make your life worth living. In due course, you're going to learn how to face challenges with a smile. On this day, when many of you are looking to contribute to the real world in different capacities, it doesn't matter what capacity it is, I'd like you to take a moment and think about what it is that you really want. What would you do for free and still want to keep doing it, even if nobody paid you for it? That is the dream that you need to pursue. Now, I'd like to take a moment and say this to all of you who are currently students at the UCE. Getting into an elite institution, of course, in our kind of society is really, really important, and it may matter a lot, but it does not necessarily guarantee success. In fact, when I joined UCE way back in 2003, not many people had even heard about this college. I was truly disheartened when people would ask me, where are you studying? And I'd say UCE, and they would ask me, where? So, it's only later on that my father and my mother taught me that it's not a college building that makes a college famous. It's students. And from that day, I have been on a mission to make the name of UCE resonate with the word success. Today, thanks to the efforts of the students, the alumni, and the faculty members, this college has progressed a lot. But there's a lot more of work that we need to do, and each of us have a mission at hand to go out into the real world and create a name not only for yourselves, but for your alma mater, for your institution, for your UCE. 2003 മുതൽ 2007 വരെ ഞാൻ ഇവിടെ ചെലവഴിച്ച 4 വർഷങ്ങൾ എൻ്റെ വ്യക്തിത്വത്തിൽ തന്നെ വളരെയേറെ മാറ്റം വരുത്തിയിട്ടുണ്ട്. എൻ്റെ ജീവിതത്തിൽ തന്നെ എന്തെങ്കിലും നേടാൻ സാധിച്ചിട്ടുണ്ടെങ്കിൽ അതിൽ ഈ വിദ്യാലയത്തിന്റെ പങ്ക് വളരെ വളരെ വലുതാണ്. അതിനാൽ ഞാൻ ഈ വിദ്യാലയത്തോടും പ്രിൻസിപ്പലിനോടും എൻ്റെ അധ്യാപകരോടും എൻ്റെ സഹപാഠികളോടും എന്നും എന്നും കടപ്പെട്ടിരിക്കുന്നു. May I also take this opportunity to wish all of the students at UCE very good luck for their future. And thank you once again for having me. It's truly an honor to have been invited to my alma mater to address the students who are currently here. Ellarkum nannu, namaskaram.
Thank you, sir. Now, I would like to invite Mr. Deepu S., Assistant Professor, Department of ECE, the Program Coordinator for delivering the vote of thanks.
Thank you. Respected Principal, respected Director, sir, and our Chief Speaker, Robin, sir, our participants, students, and my dear friends. So, this is a beginning of our session for a national level webinar series. This is just a beginning. And an ice-breaking session will be. We are having but our director was couldn't be able to join. So I agreed that he will inaugurate the session. So let me come into my point. So I would like to thank our principal, Dr. VG, to be part of this inaugural session. Thank you, ma'am. Thank you very much. Next, I would like to thank our director, sir, who was actively engaged in this webinar series and who didn't join, but I express my sincere gratitude to director, sir, also. Thank you, sir. Thank you very much. our Administrative Officer, Datta sir, our Vice Principal, Dr. Joseph Hassan sir, and our staff members. I would like to thank you all for being a part of this inaugural session. Thank you. And my dear participants, our guest participants, my students, and other friends are gathered here. Let me thank you all once again in the name of UCE and Department of Electronics and Communication Engineering. Thank you all, and wish you all a good session hereafter. Thank you.
Thank you, sir. The inaugural ceremony has come to an end. Now, it's time for the webinar on chip design in the electronic system design and manufacturing ecosystem by Mr. Robin Davis. Over to you, sir.
Hey, thanks, Aparna. And appreciate the opportunity once again. Am I audible?
Yes, sir. Audible.
All right. I'm going to go ahead and present my deck. Just let me know when you see it come up on your screens, please.
Yes, our inaugural ceremony is over and the session is going to start. Yes, screen visibility, not yet.
Yeah. Can you see my presentation?
Yes, starting. Fine.
All right.
Starting from, yes, chip design, the vital link. That is visible.
Okay. Is it a full screen presentation now?
Yes, you can proceed, sir.
Okay, great. Once again, thanks so much, everyone at UCE for having me come on board to present this. It's truly a privilege and an honor to be coming back to the place where I spent 4 years of my early adulthood, learning not just a lot about electronics system design or about electronics in general, but about life. I think the testimony which I gave for University College of Engineering a couple of months ago was a real testimony and was from the heart, given the fact that a lot of what I've been able to become today were the skill sets that I've acquired when I was in UCE. And I think all of you students who are at UCE are privileged to be in a college such as that. And if you can take advantage of the fact that you are in that kind of an institution, I'm sure you'll get to even better places. I want to see all of you flying high in the industry tomorrow. In the interest of today's webinar, given the fact that we have a reasonably wide audience, some folks from, I know that some of the folks have joined us from the industry. We have a couple of people who are doing their undergraduation and maybe even some people who are doing their post-graduation who might be joining this session today. So in the interest of everyone, I wouldn't be getting too technical, but at the same time, I'm going to try and keep it interesting for everyone. I'd be glad to take questions at the end. And if I may request all of you to keep your questions to the very end. I believe, Deepu, that's the way we've organized this particular session. Towards the end, we'll take as many questions as we need to. And then I'd be glad to taking a stab at attempting to answer them. Yeah. All right. So when it comes to semiconductor design, ever since I was in college and maybe even in school, we kept hearing about the different levels of integration, right? We had small scale integration, medium scale, large scale, very large scale, ultra large scale. Now we're even talking about optoelectronics, right? Different forms of compaction of electronic circuits into a small form factor. So what is all this fuss really about, right? If you really try to boil it down to why semiconductors is becoming more and more important today and why it's moving more and more up the value chain, it would essentially boil down to one simple thing: the use case scenario is expanding drastically. The other thing about semiconductors is that it's a horizontal organization and it caters to all the industry verticals. And what that essentially means is that today, it's not just the chip design companies like Intel or TI or Qualcomm who are building chips. It is also the large OEMs, like the family companies, for example, Facebook, Amazon, Netflix, Google, Microsoft. They're all building their own chips now. They're not depending on a Qualcomm, again, to build them a Snapdragon, for example, right? They're building their own CPUs and GPUs. So what is all this fuss about, To answer that question, I'd like to take you back a couple of thousands of years or hundreds of years to where this all began, right? where did computing really start from? Now, in the year 3000 BC, all of us are very familiar with the abacus, right? It's something that some of us use as a toy today. Some of us use it for a basic arithmetic calculator. All of us know what the abacus is. But in the year 3000 BC, this was a very, very serious device used for computing. It was used to perform very basic arithmetic operations and would essentially be able to do very, very basic arithmetic operations, and was used for extensively for trade in the US, in parts of Russia, in parts of Middle East and Europe, and also the United Arab Emirates. So at that point in time, this seemed to be one of the great computational devices. Now, fast forward to the year 1642, we all know the famous scientist Blaise Pascal. He came out with a device called the Pascaline. Now, this was a very interesting device from the viewpoint that it was entirely mechanical. It had a small rotary flywheel which you had to rotate mechanically in order for the basic arithmetic operations to be performed. And that would essentially be able to do the basics of addition, subtraction, so on and so forth. Now, at this point in time, I would say is maybe when the entire fear factor of the scientists of the, pertaining to the Industrial Revolution really began, because at that point in time, mathematicians were among the highest paid professionals, right? Given the fact that they could deal with numbers the way nobody else could deal with. And at that point in time, this was even considered as a threat by many of the mathematicians, because they were afraid of losing their jobs if the Pascalian became successful. Now, fast forward again to the year 1890, the scientist Hermann Hollerith invented what was later on called as the census tabulator. Now, this was again a very interesting device, given the fact that it was not mechanical, it was more electromechanical. And this device was very much analogous to the current day computer, given the fact that we had three parts to it. One was the input device, one was the processing device, and one was, of course, the storage device, plus, of course, the auxiliary display device. Now, the input was essentially done using what they called punch cards. Now, a punch card would be an 8x8 or an 8x12 kind of a cardboard, which would have a predefined matrix of digits on it, right? And whether there is a punched hole in the card or not would determine whether it is a 0 or a 1 correspondingly. And that would be analogous to how storage happens today, right? Today, we store information as binary information. Now, that would essentially be, the punch card would be analogous to the storage that we have today. The punching machine that's used to punch the digits or to essentially plug in the algorithm into the punch card would be analogous to the keyboard that we have today. And the device which is used to read the punch card and essentially do basic arithmetic operations would be analogous to the CPU. So you have keyboard, you have storage, and you have CPU, or rather in the reverse order. You would have a CPU, you would have a processor to process information, and you would have storage to store the information, right? Fast forward again to the year 1942, the scientist duo Atanasoff-Berry, these were two scientists who came up with what we call the ABC vacuum, or the Atanasoff-Berry computer. That's what ABC stands for. And this was essentially the beginning of the electrical revolution, where we had an electromechanical device moving to a completely electrical platform based upon vacuum tubes. This was in the year 1942 and was the world's very first fully digital computer, which was able to do very basic, again, arithmetic operations and very basic algorithm permutations and combinations. Now, this device was extremely, extremely high powered, because a vacuum tube pretty much performs the functionality of today's transistor, semiconductor transistor. And as we all know, vacuum tubes were very, very high power devices, and they would consume tremendous amounts of power, and hence the millions of instructions per second and the MIPS per second with respect to the amount of power consumed was extremely, extremely low, which would mean you need a tremendous amount of power to generate a very small amount of compute power. Fast forward again to the year 1947, and all of us know this is where we start relating the stuff, right, as electronics engineers. John, William, and Walter invented what we know today as the transistor, or the bipolar junction transistor, which was essentially the beginning of the electronics revolution. So we have mechanical, electromechanical, completely electrical, and then electronics as part of the revolution. Fast forward again to the year 1958, and that is where began the paradigm shift of moving the entire compute infrastructure to integrated circuit-based heterogeneous compute architecture platforms. And this happened in the year 1958 when Jack Kilby invented the integrated circuit. Now, as you can see, in the whole course of evolution of computing, we moved from a mechanical device to an electromechanical device, which is basically based upon relays, which essentially is an electromechanical device, which later on moved to electrical devices, which again was based upon vacuum tubes, and later on to electronic devices, which are based on semiconductors as a fundamental building block. Now, given the fact that the integrated circuit had brought in a revolutionary amount of compaction, or so many different electronic components into one single small tiny device. We all know Gordon Moore. In the year 1965, he coined a law called the Moore's law. Now, you probably have learned about this already, but what it essentially says is that every year the number of transistors on a chip or on an integrated circuit is going to double. Now, if we all understand algorithms and what hyperbole and what essentially an exponential curve would look like, this is pretty much what it would look like. It would not be a linear curve because it's double of the previous year, and the next year will become 2, 4, 8, 16, 32, and so on and so forth, right? So the number of transistors has become exponentially high, and the curve has become very steep in terms of the number of transistors per chip. So, we all may be wondering, this was defined 55 years ago. Where are we today as far as Moore's law is concerned? And if you really look at things as advanced as quantum computing, which again is very, very nascent and very, very primitive in terms of how available it can be to the public. We all know that IBM has got its own quantum computer, which is available to the public. I think they even have a website where you can actually access their quantum computer, which essentially doesn't have a bit anymore. We don't have a bit. We don't have a 1 and 0 anymore. We have a quasi-stable state, which leverages the physics behind quantum mechanics to be able to have a 1 and a 0 simultaneously. So you have a transitionary state of a bit where it is neither a 1 nor a 0, or rather can be both a 1 and a 0 at the same time. And this is best represented in the form of a qubit, which is on the screen right now. A very, very, very complex method of leveraging quantum mechanics to be able to do computational algorithms. But the advantage you have there is you have a complete paradigm shift into an extremely efficient and powerful form of computing. Again, that quantum computing is a completely different topic altogether, and which we'll not be covering here. It's out of scope of this presentation. But just to let you know that every day the way compute is advancing is pretty much beating Moore's law by the year. So the next obvious question is why so much silicon? So when I make a statement that there are so many transistors on a chip and the number of transistors is going up, why do we need so much silicon? It's a natural question. It's a logical question. I would say, as far as this is concerned, one good example for us to take would be the Internet of Things. Now, all of us knew that the Internet of Things is essentially probably one of the best use case scenarios of an electronic system design and manufacturing industry. What is the Internet of Things? It essentially means an Internet of everything, as Cisco defines it. Now, if you look at the basic building blocks of the Internet of Everything, or Internet of Things, as it's more commonly called or referred to, we have essentially 4 major parts to it. Right? We have the sense part, where we have a sensor/transducer, which essentially takes the real world inputs, converts it into a digital form through an ADC, and then essentially passes it on to a DSP or a post-processing unit. That post-processing unit would come into the thing category, which is the second bucket of devices that essentially form a part of the Internet of Things circuit. The third part would essentially be the connectivity aspect, where we have machines talking to machines. We have machines talking to people. We have people talking to machines. And we essentially have a lot of automation in the system being generated via this connect stream. The last part of it would be the act portion, right? Where essentially we are talking about devices taking the post-process information from the sensor, which is coming out at the output of the microprocessor or DSP, making sense of it based upon what is already stored in the lookup tables or the reference table with the golden models, and then making an action upon it, right? To act upon the data that we've essentially effectively brought in from the outside world. So now you expand this to all of the Am I still presenting, Deepu, or has someone else started presenting? I just got a notification.
There is an interference from one guy.
Okay.
Let me control that.
Sure. That's all right. Just let me know when my screen's back up. Do you want me to start again?
Yes, start. Now it's okay, clear.
Is it
Please
visible
start.
now?
Yes, visible.
All right, great. So
Can you expand that?
sure.
Screen. Maximize.
Is it visible now?
Not on full screen.
Okay, let me just try stop sharing and
I think it will take a while to view the screen.
okay, I think you need to give me back control. I'm not able to present it because I think someone else is presenting something. Okay, hold on. Let me just try. So you can't see anything from my screen now, right?
No.
Hold on.
Can you try it again?
Yeah, just hold on. I just close the presentation and open it up again.
Fine.
Let me just try. Okay, got it. Is it visible now?
Yes.
Is it visible now, Deepu?
Clear, clear. Okay, you can start. So other guy is also presenting. One of the guys that presenting.
Okay. Maybe we should listen to his presentation then. Is it okay now?
I think you need to start it again. Again, it is minimized now.
Okay,
Screen
just let me know. Is it visible now? Okay, let me just try closing it again. Does it come up now?
Yes, it's coming. Ah, fine. You can start.
All right, great. All right, so taking off from where we left off again. So if you take this entire structure of the Internet of Things and plug it into the different industry verticals and look at what kind of different applications we can really have for this, it's endless, right? Just to list a few of them, smart homes, we're all talking about situations where we have a thermostat, which is essentially acting as a central gateway, which talks to a refrigerator, which talks to air conditioning, which talks to every electrical device at home, and essentially can help you regulate the temperature, not only by adjusting the temperatures of the air conditioning or the heater, for example. It can also take into account the heat exchanger effects of the refrigerator or freezer that you have inside your house, right? Because those also generate heat into the environment. It essentially optimizes the efficiency and can enable a machine-to-machine talking environment. We have wearables, right? We have your smartwatches, which essentially track your ECG, your pulse rate, can track even your SpO2 nowadays, right? And can give you a lot of vital information about your general health, about your activity, about your fitness. You have smart cities, right? I don't know how many of you know this, but Hyderabad today is pretty much being defined as what we call a smart city now, because the traffic lights are in a position to have cameras which have a continuous live feed of the traffic which is oncoming, and essentially can regulate the traffic light signal based upon how many cars there are, and it will become a much more efficient regulated traffic light signal. Similarly, you have smart grids for power distribution. We have Industry 4.0, where we have a lot of industrial automation going into the manufacturing line. We have connected cars. All of us know what connected cars are now. We have A, B, C, and D. functional safety requirements, wherein it becomes just a basic ISO 26262 requirement all the way through a fully autonomous vehicle. And in fact, there's a joke saying that autonomous vehicles are no longer a technological challenge today. They are more of a regulatory challenge. It's just that the governments have to accept them and be able to have connected cars today. In fact, in countries such as the United States, we have cars delivering pizzas through autonomous vehicles, right? With a driverless car. You might have read about the Waymo, which is essentially Google's proprietary driverless car, which works based upon a LiDAR input. We have connected health. Today, we have ECG patches which sit on top of your heart and can essentially look at your ECG rate and transfer it to you via Bluetooth to your smartphone and via a smartphone through an app to a doctor. So you don't even have to go to a hospital to essentially be admitted there, even if you may be a critical heart patient. Right? You can essentially be monitored while you're sitting at home, and you don't have to keep visiting the hospital. So especially in today's scenario where people want to avoid going to the hospital, these kind of devices bring the hospital to your home and would essentially be able to help you monitor your health while you're sitting on your couch, for example. Right? We have smart retail. Today in stores such as Walmart in the United States, we have a scenario where we have beacons on your push trolleys, and these beacons would essentially be talking to your smartwatch or to your smartphone, and they would continuously monitor the RFIDs of the products which are on the shelves, and would essentially tell you that there are offers from this particular device. It would even track what you purchased the last time and say, hey, there's the same brand of Kellogg's cornflakes, for example, which is available at 20% less, which gives you much lower calorie intake with much lower sugars. It could be a sugar-free version or something that they would essentially want to push into your phone as a promotional offer. Today, when you visit an Amazon or a Flipkart and do a search for a particular product, a set of products, the very same products we can see get pushed into your social networking websites such as Facebook or Instagram or Twitter for that matter, to essentially, because the engines at the back end know what your interest areas are. So that's the level of connected smart retail that we have today. You have smart supply chain for essentially a supply chain of different products. You have smart farming. Today, farmers don't have to go out to their fields and look at how moist their soils are. They just have sensors which are embedded in the soil, and these sensors are wireless. These wireless sensors talk back to to a gateway, and that gateway talks to a farmer's smartphone, and it would essentially tell the farmer how healthy the soil is. He doesn't even have to go out to the fields anymore to see, to do a dipstick analysis and see how healthy his soil is, or how well his crops are performing. So as you can see, across industry verticals, all the way from high tech industry vertical, all the way down to all the way through to farming, which is could even be construed as something where we may not necessarily deploy much technology. Even in farming, we see a lot of technology deployment. Now, what does all of this mean for us? This essentially means one simple thing. There's an enormous amount of data that's being generated. Now, okay, there's a lot of data being generated, so what? Now, just to help you understand this, the gravity, the gravity of the amount of data that's being generated, I'm going to take you through to a case in point, right? The automotive industry. This is one of my personal favorites because the automotive industry has changed so much. Again, I would say in a hyperbolic manner, in an exponential manner over the years, and it will continue to do so. And I'll explain why. In fact, Mary Barra, the CEO of General Motors, at one point in time, the world's leading car manufacturer from the United States, had even made a statement that the automotive industry is going to change more in the next 10 years than it has in the past 50. Now, this is a very, very heavy statement. And for her to make that kind of a statement would essentially mean that there's going to be an entire paradigm shift in how people use cars moving forward. Now, this is a very open-ended statement. It could be a subscription model, or it could be because more electronics are coming on board. But let's take a look at it to see what impact it's going to have on the electronic system design and manufacturing ecosystem. Now, a couple of years ago, maybe 10, 20 years ago, when people wanted to buy a car, in fact, maybe 7, 8 years ago, when I wanted to buy my first car, what I was more interested in was how much power does this guy deliver, right? How quickly does it go from 0 to 60 or from 0 to 100? how loud is it, right? How powerful is the engine? That's how much muscle power does it have under the hood? That's pretty much what I would be concerned about. But nowadays, it's no longer just about the powertrain. Powertrain, of course, being the engine is what I'm referring to here. You have a lot more things which are being added to the automotive industry, to the extent that the powertrain is actually becoming a much smaller part of the entire automotive industry. We have body electronics, starting from your keyless entry to lane departure detection, to all of the electronics you can possibly think about. Your in-vehicle infotainment system, you have your connectivity, you have the autonomous driving aspects, which you could include lane departure or collision prevention, fully autonomous vehicle by virtue of a LiDAR, for example, right? So what does this essentially mean for us? If you take purely the numbers that we're looking at, from the year 2018 to today and beyond to the year 2025, based upon a projection of what the automotive industry is telling us today. In the year 2018, for every one battery EV electric vehicles, you would have 2.5 hybrid EVs, which will essentially be a vehicle which has both powertrains and 2 mild hybrids. Again, just for those of you who are not familiar with these terms, mild hybrid would essentially be a car which has small versions of auto start and stop of the engine. For example, I think Mahindra Scorpio essentially launched it for the first time in India, where your car is idling at a traffic light and the engine would automatically power off until you push the clutch again and the engine will power on again. Maybe a little bit more advanced version of that is what you would call a mild hybrid. A hybrid EV is something which has 2 powertrains. You have an electric powertrain as well as a fuel powertrain. It could be usually a gasoline powertrain, right, or a petrol powertrain. And the battery EV is essentially a car which has entirely, or rather only, an electric motor, right? Entirely and completely electric motor. There is no provision for you to fill it with petrol, even if you wanted to. Now, if you look at from the progression from the year 2018 to the year 2020 and to the year 2025, you can see almost a 700% increase in the number of battery EVs. What this would essentially mean is that moving forward in the year 2025, you're looking at around 33% of the total number of cars on the road, or total number of vehicles on the road, being 100% EV, electric vehicles, right? That's a big number, and a very, very significant one for us to even consider. Now, what does this essentially mean for the semiconductor industry? The more you move from gasoline to EV for a given vehicle, approximately the number of semiconductor components essentially doubles, or it increases by 100%. That's the number of additional semiconductor parts you're going to have, or electronic parts you're going to have on the vehicle. Now, how much of data are we really talking about, right? I'm using fancy terms such as autonomous driving. I'm using things such as IoT, Industry 4.0, supply chain automation. These are things that many of us, especially as many of you students, can't necessarily relate to. I'll explain to you in terms of something that you can relate to, right? I'm pretty sure all of you know these logos like the back of your hand. I've taken a couple of examples from the social media networking space, a Google search engine, and mails, right? So Snapchat, Facebook, YouTube, all of us know them. Google search is another thing that a lot of us use on a day-to-day basis. Emails, of course, everyone knows emails. If you look at the amount of data that's being generated, right, the number of Snapchats, the number of snaps, as you call them, right, is more than 2 million. You have around 3.8 million Google searches happening, around 1 million users of Facebook logged in at the same time, around 4.5 million videos of YouTube, and around 188 million emails being sent back and forth. And all of this is happening in just a minute. Let that sink in while I move to the next slide. But this is the amount of activity that happens on these logos alone in a minute. So, all right. So much data is happening. So many transactions are happening through these kind of sites. What does this essentially mean for us? Now, to quantify the amount of data for you, and for you to understand the quantum of transactions in terms of bits or bytes, or whatever it is that you want to measure it in terms of, you have a total of 40 exabytes being generated per month. Now, this seems like a lot, but just hold on. In India alone, we have around 1.3 billion people, of which a large majority of them, even though they may not have access to other basic amenities, they definitely have access to a smartphone, right? Particularly in today's scenario where the kids have to be educated through online teaching and stuff like that. So if you extrapolate this to the number of users at a global scale, where we have around 7.8 billion people as of March 2020, you can safely assume a number of around 5 billion users, right? So you multiply this by 5 billion users, that's going to get you a really, really big number. To be precise, 2.5 quintillion bytes per day is what gets generated. Right? A lot of data. And this is just from the social media sites alone. Now, all of this is fine, but what is the implication of all of this on the semiconductors ecosystem, or more importantly, the larger electronic system design and manufacturing ecosystem? Now, I'd like to start off by asking the question, was Moore a visionary? I would say he was a genius. Right? For him to be able to predict that this is what's going to happen to the semiconductor industry, he was simply a genius, right? So let's just take a look at, make an attempt to see and try and quantify whether, Moore's law is really panning out the way we expected it to. And I'm going to use a benchmark reference of instructions per second, right? You know what instructions per second are, the number of instructions that are executed in 1 second by a particular device. So ENIAC, all of us know the ENIAC. It was developed in 1946, again based upon tubes. And it was essentially a massive piece of computerized machinery, right? Or a computing machinery. It had a compute ability of around 5,000 instructions per second, consumed a humongous amount of power of 180 kilowatts, was 15 meters long, and weighed around 27,000 kilograms. It had, for all of this, it had just 800 transistors. That's it, right? Now, fast forward again to the year 1971, which is when Intel built its very first microprocessor chip, Intel 4004. All of you might be familiar with this. It had a much higher compute power of around 46,250. Could swing all the way upwards to 92,500 instructions per second based upon the upswing of the clock frequency, or whether it goes into overdrive or not, based upon the kind of operating frequency and corner that you wanted to operate it in. But essentially, it consumed only a power of 1 watt, right? Just look at a comparison of 1 watt versus 180 kilowatts. Right? It had a die size of only 12 millimeters square, and had a much higher number of components, almost 3 times the number of transistors. It had 2,250 transistors on board. Now, hold on just a minute, and let's take a look at the world's biggest ever die that has been manufactured. When I say die is essentially the internal part of the chip. What you see here on your screen is actually the packaging, right? You essentially have the die, then you have the wire bonding, and then you have the packaging on top of it before it goes into the PCB or into the socket, or the SoC goes into, we call it a socket, right? But this is essentially what the overall chip looks like. Now, what I'm talking about is the largest die in the world to be ever manufactured, right, in the history of semiconductors, was built by a company called Cerebras, WSE, in the year 2019. Now, just look at how big this device is. I've actually put a golf ball nearby the wafer just to show you how massive this die is, right? This device is the biggest ever die manufactured in the history of humankind till date, of course. It had a massive compute power of around 100,000 terabits per second. Obviously consumed a high amount of power at around 15 kilowatts. Again, a lot less than 180 kilowatts of ENIAC. It had a die size of around 21 centimeters by 21 centimeters, or 215 millimeters by 215 millimeters. It was manufactured on TSMC's 16 nanometer FinFET. 16 nanometer here is the size, or is the length of the entire gateway, is the length of the entire transistor in terms of size. TSMC, you might be aware of, is Taiwan Semiconductor Manufacturing Corporation, and it had around 1.2 trillion transistors on board. This corresponded to around 400,000 cores. Now, as in when you guys get into the semiconductor industry, you will be able to appreciate how massive and what an engineering marvel this particular die is, given the fact that it has 400,000 cores on board with 1.2 trillion transistors. Surely the amount of crosstalk, the amount of power that's being generated for you to be able to control that power to essentially spread it out across the wafer in such a way that it doesn't burn out the chip is truly phenomenal. So this is where we stand today in terms of technological ability to compact a large number of transistors or capacitors and inductors, or basically your active and passive components onto a semiconductor die. Now, Moore's law, all of us know, states that the number of transistors doubles every year, but the less talked about law, which is called the Rock's law, also states that the cost of fab doubles every 4 years. Right, and just to give you a rough ballpark of fabs would essentially be the companies such as TSMC or GF Global Foundries or SMIC or UMC or even Intel, for example, right, or TI, which have their own custom fabs. These would be the fabrication companies which would essentially take the GDS2 and put it onto a die and manufacture the chip. The cost of a fab today is around $20 billion. That's what it stands at today. So I just wanted to bring this particular point up just to let you know that semiconductor design is great, but it's a costly affair, and which is the reason why semiconductor industries engineers are carefully chosen from engineering colleges and from the industry, because one small mistake could cost them it could be a multi-million-dollar mistake. All right. Of course, not to scare you much, there are enough checks and balances in the entire flow of building a chip to ensure that we catch a bug in its earlier cycle, just to let you know that it's an expensive affair. Now, since all of us are pretty much interested in knowing where, I'd say the large majority of us in today's webinar would be interested to know what's in it for me. All right, all of this is fine. This is really fancy data, but where do I stand? Where do I go? Do I join the semiconductor industry? So I'm just going to try and give you a bird's eye view of what the semiconductor industry is today in terms of the step-by-step process of how you build a chip, right? So that you can get to know what it takes to build a chip and whether you really want to be a part of this ecosystem. Now, it all starts with the users like you and me, right? So tomorrow, I may not want this particular phone. I may want another phone. I may want a phone which has a more processing power. I may not like Face ID. I may want something a little bit more augmented in terms of reality, right? I may want more processing power in terms of augmented reality. I may want to be doing Bitcoin mining on my phone. I may want to be doing many other things with respect to computational algorithms on my phone. And based upon that, I as a user get to choose what the OEMs should be influenced into manufacturing. So the users essentially define what it is that the next big thing should be for the OEMs and the semiconductor companies to build. Based upon the inputs from the users and the market analysis that happens, the business analysts essentially who are part of the company, who are talking to the marketing interface, would gather this data, would try to assimilate it and build a plan around saying, okay, so this is what the users are going to want tomorrow. So this is what we essentially need to build in order to become successful in the industry. They then proceed to build the architecture of the chip. And what the architecture would essentially comprise of is it would say, okay, I'm going to have a bus or a NOC, which would essentially come in an AMBA kind of an architecture. I would have so-and-so peripherals. I would have the USB 2.0 or 3.0. I would have the HDMI 1 or 2. I would have PCI Express Gen 3, Gen 4, Gen 5. Essentially a choice of the bus architecture, the microprocessor, the peripheral, and essentially say how these are going to talk to each other and form the overall integrated system on chip. Then, of course, it would generate what we call a specification or a PPA document, specification and a PPA document. And the specification, as you all might be aware of, is essentially the document which says, okay, this is how big my chip is going to be. This is what the floor plan is going to look like. This is where each IP is approximately going to be. This is the functionality of my chip. When I give this particular input, this is how the read-write cycles are going to happen. This is how the processing is going to happen. This is how the interface is going to happen to each of the IPs. And this is how the output is going to finally happen. And this is going to be the use case in certain cases. PPA, again, is a very, very important terminology used in semiconductor design, and it stands for power performance area. I'll say again, power performance area. Power performance area would essentially be the three most important parameters of a chip. And when you're building a chip, this is what would be of utmost importance. Power would be the amount of power that it consumes. Performance would be its frequency of operation, essentially, which would essentially mean the higher the frequency, the more the instructions per second, and so on and so forth, without burning the chip out, of course. And of course, the area, which would be the size of the die, per se. Now, all three factors have a trade-off on each other, right? The more the frequency, you would all know, the power, the more the power. The more the frequency, the more the power. So if you want to have it on your mobile phone, for example, you can't be overdriving the chip at too high a frequency. You cannot be consuming too much power because then your battery is going to run out soon, right? Similarly, your area is another function of your performance, right? You can have a massive A57 Cortex ARM A57 chip, which essentially goes onto the SoC, but that's going to take a lot of power, right? And that would essentially not be, that would essentially again dry your battery out quickly. Again, I was talking about area, right? A massive A57 is going to have a large number of logic gates, which would mean a larger footprint on the real estate of the chip. So each of these have a trade-off between each other. So once we optimize on that based upon the end use case scenario, so automotive would be different from industrial, would be different from, should be different from healthcare, and so on and so forth. Once we finalize on the specification and PPA, we get into what we call the RTL to GDS flow. Now, RTL, as the electronic students might be aware, stands for Register Transfer Logic. And this would essentially be the software code that you write for deciding the functionality of each of the IPs or of the SoC. Now, you would take it through a couple of steps, including steps called synthesis, which is when you would move the RTL from RTL stage to a gate level netlist. You would be do static timing analysis, or STA, which would essentially give you the timing parameters of the chip and which would help you understand how the chip is going to behave in the real world scenario. You would do things such as scan insertion. You would do things such as MBIST insertion, which would insert the things such as the controller, the memory controller wrapper, which would be able to do an MBIST or a built-in cell test of the memory or the crucial memory where the opcode essentially lies when the chip is in operation, before the chip, or just soon after the chip powers up, before the system goes up into operation, right? For example, it would also bring more controllability onto the chip. It would be able to help you understand whether a particular bit inside the chip is stuck at 0 or stuck at 1 or hanging as open, for example, right? When the chip is out, because when the chip is out, it's essentially a black box. You would be doing things like parasitic extraction, where you essentially measure the parasitics on the chip, such as the inductance, the capacitance, and so on and so forth, the resistance on the chip, and would essentially do an analysis of those stray characters, the parasitic characters, which would essentially be very, very crucial in optimizing the performance of your chip. And finally, the end product of your digital circuit design would be what you call a GDS. Now, GDS is essentially a database which goes to the manufacturing hub just before, in order for the manufacturing of the chip to happen. While this digital design cycle happens, we also have the custom design, a very similar kind of flow, but the difference is that the custom flow is usually done for the analog components of the chip, which are the parts that are interfacing with the real world. For example, the analog to digital converters, the LDOs, the PLL, the phase lock loops. These are all analog components and would essentially require a transistor by transistor level design of these components, of these particular parts, in order for the performance performance parameters to be met. That would also lead in what you call a netlist. Once these two netlists are available, we would integrate them together into what we call an integrated SoC GDS. So you would have the digital part, you would have the analog part, and you would integrate the two together to form an integrated SoC GDS database. This GDS database is something that you later on would take through a couple of iterations. It will go back and forth based upon. So at every stage of the process, we do something called verification/validation. Now, verification or validation is essentially a process by virtue of which you check the functionality of your output. It could be an RTL, it could be a netlist, it could be a timing annotated netlist, or it could even be a GDS, right? To essentially benchmark it vis-a-vis what we have defined in the specification and the PPA document, right? And essentially take it through this iteration. Sorry, one thing which I forgot to mention in the RTL to GDS process is the place and route, where once we have the netlist, you place them as different blocks around the layout within the footprint of the chip, within the pin layout of the chip, and essentially connect them to each other, which is called the routing. So the placement and routing of the chip. And then, of course, you do a physical verification of the chip, which essentially is a benchmarking of the physical layout of the chip versus the design rule deck or the rule deck which comes in from the fab, such as, for example, if TSMC is going to be your fab, TSMC would initially issue a rule deck which would help you understand whether every part is built within a particular set of parameters, whether the vias or whether the interconnects or whether the die is essentially oriented in a way that is going to be feasible for the manufacturing entity to be able to bring out these features on the chip the way it is supposed to be. So essentially a design rule deck is issued from the fab. That essentially is called DRC or design rule check, or LVS, layout versus schematic check, that is done. And once all of this is complete and we are confident that the GDS is ready for fabrication, what we do is we send it for generating what we call a photomask. Now, all of us, the folks who are studying electronics engineering are probably familiar with the photolithography process, which would essentially be, you would have a photomask, which is essentially the negative print of your integrated SoC GDS, and which would help you do the etching and the doping of the semiconductor wafer. Once the photomask is ready, we get into the entire process of manufacturing. Now, let's take a look at what happens in manufacturing, right? We might be familiar with the silicon ingot. Silicon ingot is nothing but the purest form of silicon that's available. It's a pure silicon crystal. It would contain 98, 99% upwards of pure silicon on it. And the manufacturing process, of course, is something I'm not going to really get into because it's not really something that we would be interested in knowing about at this stage. But what the silicon ingot would essentially be manufactured in a cylindrical form. And there's a reason why we do that. The cylindrical format's cross-section would be a circular form, and that is what we would be using as a wafer to do the doping and to be doing the die manufacturing. Once the silicon ingot is ready, we slice and polish the wafer. As we slice the silicon ingot in order to get the wafers, and then we polish the wafers. Right? These wafers are then later on taken into the process of the etching and doping process, wherein the photomask is used to essentially selectively shine UV light on different portions of the die in order to dope, in order to etch, and then further on dope different portions on the chip to translate your GDS onto the physical form of your die in the form of transistors or diodes or both. Soon after that happens, you have your GDS printed onto your wafer. Or rather, you have the 3D version of your GDS design on your wafer. And once that's ready, it'll look essentially something similar to what's on the screen right now. It would be, if you look very carefully, you can see these small rectangles and squares, which are nothing but your IPs or your different your building blocks in the chip. And you have multiple such dies which are stacked side by side. So what we do is we then cut this die, and then we test the die as a die itself, even before it goes into packaging. Once the die is cut and tested, we take it through packaging and validation, and this is essentially a process where we do a wire bonding of the portions on the die out using gold or silver wire to the outsides of the package. Right? Earlier, when I explained the Intel 4004, I was explaining to you that is actually a package that you see. The black thing that you see on your PCB is actually the package of the package of the chip, and the die sits inside and is wire bonded to the external package. Once the packaging is done, you do the validation, and soon after that's done, you will get an SoC that's ready for system integration. I've taken the case of Intel's Core i9 and of course Radeon from AMD, a CPU and a GPU, plus the case of two critical parts of heterogeneous compute architecture in today's compute scenario. So this is what your finished product would essentially look like. Now, what happens next, right? It goes into the system for integration, and then it comes back, you're right, to users like you and me, and then we say, hey, you know what? I think I like this new feature. Maybe it should be there for the next device. And then the entire cycle repeats again. So as long as there is a demand from the user base, there will be a supply. Right? It's as simple as that. Now, moving to how do EDA companies help? So EDA stands for Electronic Design Automation. Companies like Synopsys and Cadence and Mentor are essentially EDA companies that build the tools and build the IPs that essentially go into building these SoCs. The critical parts for EDA companies would be IP, the intellectual property, which would be things such as the processors. ARM is an example of a processor company, but Synopsys and Cadence also have their own IPs in terms of processor. We also have the PCI Express IPs. We have things like USB, we have SATA, we have things like SPI, I2C. Any of the IPs which go into the SOCs, SOC as building blocks would essentially be, or rather many of them are built by EDA companies. Then of course you have the PCB or the printed circuit board or MCM. Now PCB is something that all of us know about, we're probably familiar with it, but multi-chip module again is something that will essentially have what we call an interposer or different other kinds of methodologies or technologies, by virtue of which you have two different dies, the die that we saw in the earlier slide. You have two different dies either stacked side by side, which will enable to use an old die with a new die. So you can manufacture a new die with new functionalities and have it interposed with an old die. This would essentially help you to be able to save on building a new die, and would help you to add just the delta components onto an old die. It could be a die-to-die stack like this, or one on top of the other, or side to side, and all of this would have the die-to-die stacking would happen within a single packaging. So that is what you would essentially mean by MCM. So those the tools in order to build MCMs are essentially also supplied by companies in the EDA spectrum. CAE again for system, logic and transistor level design. Design and verification, which would essentially be the physical design and layout of the chip. Then of course consulting. Consulting is a very tiny piece. It's not like the services companies supply a lot of manpower to the industry. The consulting bit is because companies like Google and Microsoft and Intel and TI use tools from, for example, a company like Synopsys to build their chips, right? And these tools, since they're coming from us, since we build the algorithms behind the tools, we would be the best people to tell them how to optimize the usage of those tools. From that perspective, consulting would also have a thin layer of consulting, maybe a couple of consultants for a customer is what we would essentially optimize on to be able to help the customer integrate the SOC effectively and to be able to bring the different parts of technology together. Now, among these five, CAE and design and verification would essentially form obviously the VLSI CAD or EDA. CAD again is computer-aided design or electronic design automation piece. The VLSI piece would be CAE and design and verification. Now, the Electronic System Design Alliance categorizes EDA tools into multiple categories, right? In the interest of time, I'll just run through them. We have two buckets, mainly analysis and synthesis. Analysis would essentially be the part where you analyze parts of the chip, where you do things like simulation or validation to check whether your functionality is really working based upon benchmarked vis-a-vis what your design has actually come out to be. It could be an RTL level, it could be a gate level simulation, so on and so forth. It could be a logic simulation, it could be a circuit simulation where you have a schematic based on transistors for custom design and you validate. That could be static dynamic analysis, power analysis to see how much power the chip is actually dissipating at any point in time. DRC, as I mentioned, based upon the rule that comes in from the fab, you do a design rule check to see whether it is, there's a synergy between the physical layout of the chip and the rule deck that comes in from the fab. Parasitic extraction would be with respect to measuring your inductance, capacitance, kind of your passive component parameters, which will be inherent on the chip, and naturally given the fact that it's a physical device. And again, then you move to the synthesis part, right? So analysis is more of the simulation, the validation to check the check and balance category of products. Then you have the synthesis set of products, which would essentially be the physical implementation part of the products, which would be things like synthesis. Synthesis would be where you convert your RTL into a gate level netlist. Floor planning, which is where you would place and route different blocks around your layout. Then of course you'd have mask data preparation, which would again, as I mentioned, which would help you in photolithography to know where to etch, where not to etch, where to dope, where not to dope. Then of course your optical proximity correction. Now this is something which is interesting and which will essentially come into play when your transistor node becomes smaller and smaller. So we started at 1 micron and above, then you move down to 90 nanometers, 45, 40 nanometers, 22, 20, 16, 14, 10 nanometers, 7 nanometers, 5, and now we're even at 3 nanometers, right? There are a couple of test chips which have been manufactured on 3 nanometers. So the smaller your transistor becomes, the more difficult it is for your photomask to be able to lay. For example, we have an L and you have a light shining through it, and when your size becomes smaller than the wavelength of the light that you use, your light starts dispersing. And so you would have to use things such as double pattern correction, so on and so forth, to be able to do the optical proximity correction in order for the for the etching and the doping to happen effectively on the chip as you would want it to happen. These are just a few of the many tools that EDA companies essentially, you have things such as 3D IC from companies such as Synopsys, which would be able to help you build three-dimensional ICs. You have things such as FUSA, which again Synopsys is a tool that Synopsys provides to companies such as Continental, companies such as Infineon, which build automotive-grade chips, and they would essentially do the functional safety, help you take care of the functional safety aspects of building a chip, which go under the ISO 26262 compliance umbrella. It could be under the hood or within the cabin, wherever it may be. There's a huge plethora of tools that essentially EDA companies would be able to supply to the market today and continue to help the semiconductor companies build chips with. So there are, as per the ESDA, there are today around, I'd say slightly more than 30 categories of tools that would come under the bucket of EDA tools. Now, this is a question that I get quite often, right? Given the fact that today AI seems to be solving everyone's problems, right? Does AI necessarily help in electronic design automation? Let's take a stab at that one. Now, just to give you a quick analogy, on a chessboard, you have close to 64 squares. You have a couple of pieces, and the number of states you would have there is 10 raised to 123, which would be around 41 zeros. Moving to a Chinese Go board, the number of states would be around 10 raised to 360, which is 120 zeros. Now, in a placement scenario, this is what a typical floor plan would look like. In a place and route scenario, in the physical implementation of a chip, you would have more than 10 raised to 100,000 states, which is a lot of zeros, right? So just to let you know the number of permutations and combinations that are essentially possible when you go from something as simple as a chessboard all the way through, something as complex as a multi-million gate SoC design. So in this entire process, maybe at the top of your head, based upon what I just explained to you, what would occur to you is that there are three main areas where we could potentially maybe use artificial intelligence. One would be implementation, one would be sign-off, and one would be verification. Given the fact that there's a lot of reuse, there's a lot of data that we get, there's a lot of data which is repetitively used across different designs. But just to help you understand whether this really is going to help, I would want to define what essentially would define whether AI would solve a particular problem statement. There are three parts to analyzing this, right? So as we all know, an artificial neural network is something which would essentially learn to be able to perform a particular action based upon the repetitive amount of data that you give it during what we call as the training period or the learning period, right? Now, that would essentially boil down to three key parameters: the nature of the problem, the availability of the data that's at hand, and of course, how often does the technology node necessarily change? In a semiconductor kind of scenario where your technology changed drastically, which means your design rules from the fab keep changing, which essentially means your DRC keeps changing, which means everything in the entire cycle keeps changing. There's a lot of delta which essentially happens there. So the amount of reuse that you would necessarily have in an SoC design cycle may not necessarily be as high. Having said this, there are certain SoC designs such as derivative designs where you have a master SoC platform and then you want to remove a USB 2.0 and bring in a USB 3.0, right? Or you want to move an HDMI 1, you want to bring in an HDMI 2. As easy as it sounds, you would have to run the entire chip through a regression of RTL, GDS, as well as timing annotated simulations at the block level, subsystem level, as well as the SoC level in order to ensure that the chip is working as per plan. And what that would essentially mean is that specific to the larger part of the design minus the changed part of the design, there is a lot of reuse in the static timing analysis constraints, in the synthesis constraints, in the floor plan, in the pin map. So many of the things are the same. So you can actually reuse a lot of it. And from that perspective, maybe AI could help. Where AI really does help in an EDA company is the way a particular chip is placed and routed, right? Or the way a particular block is placed and routed, or the way a particular timing analysis is done for setup or hold violations in a chip is essentially based upon a certain set of thumb rules, or the algorithms which are driven in the chip can leverage a lot of AI. a lot of artificial intelligence, because the algorithms are working on multiple designs, and the fundamental principle by virtue of which it does this optimization, again, it keeps changing, but there's a lot of AI that you can essentially use to build the algorithms that constitute the brain of an EDA tool. Which is the reason why Synopsys, for example, has a dedicated AI team which continuously tries to leverage the advantages of using AI in implementing its tools. In fact, we've even come out with an integrated platform called Fusion Compiler, which does everything from RTL synthesis all the way through GDS2, including your synthesis, your test insertion, DFT insertion, your static timing analysis, including place and route, including parasitic extraction, physical verification. It does the entire gamut of activities in order for you to be able to deliver the final GDS netlist to the fab. So, in a nutshell, yes, of course, it does help EDA companies, and this is essentially how AI helps EDA companies in the entire process. So, I'm guessing that most of us who joined today's seminar have joined this seminar to know what's in it for you, right? Because when I go to a technology summit or a technology talk, the first thing I ask is, okay, what's in for me? Is it going to help me in any particular way? Apart from the awareness of the technologies that are out there, how is it going to help me in my career? Is what I would ask. Ask myself. In order for us to gauge that for any industry, for that matter, right? It could be any industry that you want to get into. You may not be wanting to get into semiconductors or electronic system design, manufacturing per se. Whichever industry, it could be in avionics, it could be in automotive, it could be in industrial automation, it could be energy and utilities, it could be in fashion design, right? Whatever it may be. The first thing you need to do is you need to check a parameter called TAM, or the total available market. This would essentially tell you the amount of business that this particular industry is generating today and could potentially generate tomorrow. Then the other thing you need to do is check how this particular industry is going to grow into the upcoming needs of the user base, users like you and me, right? So to define this for you, the entire revenue today that's being generated by all the EDA companies today is a significant yet not too large, close to $12 billion, right? And this is growing at a rate of 8.4% year on year. I'm not getting into the details of the split, but this is just a basic split on how the SIP is soft IPs, IC design verification, we know what it means, PCB and MCM, CAE, and of course, consulting, right? Now, how does this tie into the entire ESDM value chain? The EDA and IP business constitutes only around $11.9 billion. The embedded software comprises around $11.6 billion. And in comparison to the foundry business of $76.4 billion, the semiconductors industry overall of around close to $450 billion, and the electronic system design manufacturing ecosystem, which will include all the OEMs, all the tier one companies, of around 1.5 trillion US dollars, is quite small, right? EDA and IP may form the smallest part of it, but I would like to see it as an inverted pyramid, wherein EDA and IP forms the heart of the entire ESDM ecosystem, and it's probably one of the most important parts of it. So this is essentially the entire revenue landscape of where the ESDM value chain lies. So each of these parts of the value chain would be extremely, extremely important, because the entire ESDM value chain operates as a horizontal organization and caters to all of the industry verticals, because you need electronics in healthcare, you need it in energy and utilities, you need it in backplane management, you need it in farming, you need it in every possible industry, in automotive, in aviation, every possible industry you can think of. Now, just to help all of you understand a little bit more of where a company like Synopsys would essentially contribute, I'm going to just stop presenting and show you.
Presentation stopped, but we are moving
Yeah,
to the video.
I'm gonna share. I just want to share with you.
Present now and share.
Okay, just 1 second. Let me just stop.
When I wake up,
can you get the audio?
off my smartphone, all of those electronics.
Can you maximize that? Yes, clear.
Day, Synopsys is at the heart of.
Let's start it once again, please.
When I wake up, when my alarm goes off on my smartphone, all of those electronics, anything that you're interacting with every single day, Synopsys is at the heart of.
Synopsys is the lifeblood of technology. We are the building block of just about every electronic device and integrated circuit and chip that's created.
I might make a cup of coffee or get on my computer, check my email.
Technology is in our DNA. We always want to be the best at what we do.
And Synopsys is really a driving force in the wave behind the technology.
I drive to work every day. Synopsys touches safety systems, power steering, entertainment. We're creating the software that goes into those chips.
We're providing solutions that help our customers accelerate their innovation.
Anything that has a chip in it, Synopsys is there.
We really do drive this technology forward.
We are the heart of high tech. Synopsys is actually accelerating the innovation.
You can't get any more cutting edge than that. Whether it's the latest cell phones or the latest tablets or the latest cloud computing, we're using Synopsys tools and technologies to enable those designs.
We are everywhere.
Accelerating innovation.
You're using Synopsys technology.
Yeah, that was a nice video.
Okay, just gonna go back to my presentation.
Yes.
Just one second, I need to close it and open it again. Is it back, Deepu?
Yeah, full screen present.
All right, great. So all of this is great, but at this juncture of your life, particularly the students, you'll be wondering. Sorry. At this juncture in your life, you would all be wondering, where should I head? This is great, but I'm all the more confused now. Probably when I was an engineering student as well, I was maybe even more confused than all of you. But one thing that I learned in due course, which is something that I said during my keynote, and which is something that I try to stress on, and I can't stress on enough, is that what really matters at the end of it all is what is it that you love to do? What is it that you want to do every single day? What is it that you want to jump up from your bed from every day for and do without even asking a single rupee for it? From that perspective, I would go with one of my favorite marketeers / engineers / technologists, Steve Jobs quotes. And it basically goes to say that your work is going to maybe fill the biggest part of your life moving forward, right? And the only way to feel truly satisfied is to do great work, or rather to do something that you believe is great work. And the only way to do great work is to love what you do. So if you haven't found it, keep looking. And last but not the least, do not settle. Just to help you understand where I'm coming from, when I graduated from the Mahatma Gandhi University College of Engineering in the year 2007, I was blessed with a couple of placement offers, and I chose to join Wipro's VLSI division, and I was working with a client called TI, or Texas Instruments, in their automotive chip design division as a consultant. So at that point in time, I love the technology. I love semiconductor design. I didn't really understand much of it, but as the years went by, I understood more and more about it, and I understood the impact that it has on the overall industry. And what I decided is, this is something that I want to do, but not as a chip designer alone. I want to go up the value chain and talk business, talk technology to customers. And I started off as a chip designer, but right now I pretty much manage the business for a couple of tier 1 American and European clients for Synopsys, because that's what I love to do, right? It may not be something that you love to do. So thereby, I get to talk technology, I get to interact with people, I get to strike multi-million-dollar deals with people. It's something that drives me forward every day, right? When I sign a $100 or $200 million contract, $200 million contract, it's something that gives me a blood rush like none other, right? It gives me that spark of energy. So similar to that, you will in due course find what it is that you love, and these kind of presentations will essentially open your eyes to possibilities of what you could essentially do. But at the end of the day, each of us is different, and what I love may not be what you love, and you have got to go out there and discover what it is that you love. So I'd like to close this session by saying good luck to all of you, and I hope to see you all in the semiconductor industry, because I know a lot of bright minds come from a college such as good as University College of Engineering, and so I'd love to see many of you in the industry. Good luck to all of you, and thanks so much for having me once again. Deepu sir, I'm open to questions now.
Yes, sir. Thank you very much. That was a mind-blowing session from you. What a technical talk it was. Very interesting. So you started from the Moore's law and electronic design automation and all the steps. And there is a gap that exists between the academics and industry. That's what you are focusing on, and you are bridging the gap between academy and industry. So we hope this session. Let me ask the queries from participants side. All the participants, please post your questions on chat box.
Yeah, before you do that, Deepu sir, I know there's a lot of hesitation for students to ask questions. So my humble request to all of you is please see me as one of you. I am still one of you, and I'm always right there with you in the same boat. There is no bad question at all. So please feel free to ask your questions either now or later. I will share my email ID with Deepu. Please connect with me over email or over LinkedIn. I'd be glad to answer your questions and essentially mentor you, because I have been blessed with a lot of mentors who helped me mitigate my way through the industry, and I'd be glad to be one of them for you. Yeah. So please go ahead.
Yes, and we are proud to be a UCE, and we got a UCE like you over here for the session.
The honor is mine. The honor is mine.
Yes, please, the participants, please respond through the chat box. Also, you can unmute and ask this question directly. Please respond. I think all are busy with filling the feedback form. I will give you time. Don't worry, feedback forms can be filled later. Please respond to the queries. Make some queries here for all you. So we are waiting for the questions. Robin sir, hope you are watching the chat box for the questions.
Yes, I am. I do not find any questions. I see a lot of thank yous, a lot of yeses, no sirs.
All the participants, please respond. Question session is open to all.
If you don't want to post it in chat box, just open up your mic and ask it directly. That's also fine. Either way, so.
Just shoot your questions, please. Yes,
okay.
One
question from Elna. What is the current nanometer technology going on in research? Good question, Elna. Thanks for that question. So, I'd say from 16 nanometers onwards, 16 nanometer TSMC or 40 nanometer Intel, we moved into a new kind of 3D transistor or 3D FinFET technology, we call it the FinFET technology base, right? And downwards from there, it's all 3D transistors or FinFET transistors. As of today, most of the fabs are equipped with technologies up to 7 nanometers and 5 nanometers. The newest technology node that we're envisaging into, and which has, I think, recently Samsung had a tape out on that technology node, it's 3 nanometers, right? Now, each of these technology nodes also have their own power performance area and challenges. But essentially, today, as of today, to answer that question, it is 3 nanometers, and there's even a lot of research going on below 3 nanometers. But as of today, the tape out that has happened is on 3 nanometers. Yeah, I hope that answered your question, Elna. Was there a follow-up, or is that clear enough?
And there is a query on your email ID.
Oh yes, I can post it in the email in the box.
Yes, sure. So Elna replied as okay.
There you go. That's my email ID.
Yes, please note that email ID in the chat box. And another question. Okay. What are the challenges of nanotechnology development in COVID pandemics?
Interesting question. So I understand the question from Sharon is what is the impact of the COVID-19 pandemic on the semiconductor industry in general or the development of new technologies? I would say that it's business as usual. As far as the R&D is concerned, as far as the new technology development is concerned, given the fact that we are, an EDA industry at the heart of all semiconductor design and manufacturing, I can confidently tell you that semiconductor companies obviously are rehashing their business requirements and are trying to essentially reprioritize their designs. What that means is that the tier one companies like Intel, Qualcomm, TI, for example, or Cisco for that matter, are essentially trying to spend less on products which do not have an end customer, or which are just being built for the sake of a catalog product, right? To put on their catalog, which don't have an end customer. So only those designs which have a definite end customer are being focused on today, and the other designs are essentially parked aside. So what that essentially means is that for the services companies, there may be a slight impact because the catalog products or the derivative designs, derivative designs is another one, a category of designs that may not necessarily be on in a full-fledged manner. But those kind of designs would kind of slow down a little bit, given the fact that companies would want to reserve their cash for doing R&D work for a new industry segment, such as healthcare, for example, it would come up, right? So definitely the COVID-19 pandemic has had an impact on the semiconductor industry, but I think it's largely business as usual till now.
Thank you, and thanks for the question, Sharon's career.
I hope that answers your question, Sharon. If not, please follow up with another question or unmute yourself.
Yes.
Another question from Solomon Joy. So, why major companies depend on Qualcomm instead of investing on their chipset for mobile phones? Yeah, good. That's a brilliant question, Solomon. And I'm impressed to see this kind of a question from. I'm not too sure whether you're a student, but well done, man.
Yes, it's the student.
Great. So that's a great question, and I understand where you're coming from, Solomon. You're right. In the earlier years, many of the OEMs would depend upon a Qualcomm to deliver the next version of Snapdragon, for example, right? And that still is the case even today for many of the OEMs who are trying to get maximum bang for the buck. So, for example, companies like Xiaomi. Many of the tier 2, tier 3 mobile phone manufacturers still depend upon, let's say, for example, a Qualcomm to build their chip. On the other hand, there are also companies like the FANG league of companies, right? For example, Facebook, Amazon, Microsoft, right? Google is. I'm going to give you the example of Google. Google, starting the year 2017, if I'm not wrong, 2017 or 16. Pardon me if I'm wrong there on the year. Started building its own semiconductor chips. And they started off with designs as complex as GPUs or the graphic the graphics processing units, right? The GPUs, which would essentially help them to get better graphics to the screens, a better user interface. But in due course, what happened is they started moving more and more towards the microprocessor, the L1, L2 cache memory, and the entire semiconductor chipset on the phone. Now, in the latest Google Pixel phones, which is their flagship or their sweet spot smartphone coming in directly from Google, most of the key chips are actually built by Google. Another classic case is Apple, right? Apple is also building their own semiconductor on their devices. So you're looking at a paradigm shift where chip manufacturing companies are more building general purpose MCUs or application processor, right, units. Whereas the companies like Apple and Google, which can afford to target a more premium user base, people who can afford a Google Pixel or an Apple iPhone, they are investing more into building a better performance chipset for their customers, because they want their customers to essentially be able to target a much higher performance in something which is truly unique, something which nobody else even has before, within the compressed form factor. So yes, many of the companies still depend upon chipset manufacturers such as Qualcomm. Not just Qualcomm, we have the NVIDIA Tegra, we have many other application processor manufacturers. We have TI's OMAP, for example, right? I think they stopped at the OMAP 4470, and I think 5 and 6 didn't come out. But many of the semiconductor companies have their own chipsets, but today OEMs are moving more and more down the value chain to essentially ensure that they have their own chip design teams. In fact, Thodupuzha even made a press release stating that he's going to move his entire Google chip design team to India. Right? I am working closely with Google today. We are working closely with Google in India today to help them build cutting-edge, top-notch semiconductor designs in India with Indian VLSI engineers. So great question, and thanks for that. But to answer your question, while there will continue to be a market for semiconductor companies like Qualcomm, I think we should also understand that OEMs are actually building their own silicon. It's all about a trade-off between, if I invest 50 million, it will cost around 50 to 60 million dollars to build a chip. If I invest $60 million in a chip, how do I amortize that cost to break even and to essentially get the profit back from my customer base? Right? It will depend upon that, and that's how they are optimizing on their semiconductor design. But slowly, I am noticing a paradigm shift in more and more OEMs coming on board the semiconductor ecosystem and building their own chips. I hope that answers your question, Salman. Sharon, I didn't quite understand your question. The impacts of technology. If you could just rephrase that question while I answer the next question, please, that would be great. If a new company were to enter a semiconductor industry, would it survive? Fresnel. Interesting question again. That would again depend upon which industry you are getting into or which industry vertical you are catering to. I can give you a lot of examples of startups who are essentially building their own chips. You may not have heard of a company called Acronix, for example. This particular company specializes in aerospace-grade backplane FPGAs. We all know of Altera and Xilinx, right? But how many of us know about Acronix? They have cutting-edge technology designs, customized FPGAs with a lot of programmable circuitry on the FPGAs, targeting aerospace-grade designs, which is very, very high-performance designs. Not many of us know about them. They're a great company, right? Again, Cerebras, the classic case of the company which I just told you about, which has built the world's largest die ever. They are a startup, right? So there are many startup companies who are still building products. And what essentially happens is these companies either come up with a great product for themselves, which either get bought by a larger company, or they sell their own product and become big. Another classic case is Emilex, right? Emilex was later on brought by Avago/Broadcom, and now is part of Broadcom. Right? They made a lot of money when they sold that, when they went over an IPO. Now, if you're talking about the services segment, there also we have a lot of companies. I think the number of, we have probably 200, 300, or maybe even more than that services companies in India catering specific to the semiconductor services industry, right? So there's a tremendous amount of scope. It's all about how you get into the industry with a proper plan, to amortize your investment in the company and to be able to break even and start making a profit and to sustain. I think it's all about getting into an industry where you can have a sustained growth of your product or service, either one of them, catering to one or multiple industry verticals, and essentially it will help you continue to grow. So I would say, if you're planning to, from your question, I gather that you might have a thought to start your own company. If you're doing that, please gather your thoughts around how you're gonna, break even and start making a profit. And more importantly, what your exit plan is. Are you trying to go IPO? Are you trying to sell the company? Are you going to try to create a buffer stock to be able to go into a joint venture? What is your exit strategy? I think once you have the entire plan in place, and if you see a market space, then I don't see a reason why anybody can't start his own company today. When India dominates on this sector, I'm guessing what you meant is, will India dominate the sector? Well, to answer your question, the number of semiconductor engineers in India today is extremely, extremely high. I don't want to put a number to it, but it's in tens of thousands of engineers today, right? When I graduated from my engineering college, I think it was probably a couple of thousands, maybe a couple of hundreds that were there in India. But today it has grown again exponentially, just like the Moore's law, just like Moore's law has essentially talks about the growth in number of transistors on a chip. So yes, India does have the potential to dominate this particular sector, but I would say the only missing piece in the entire ecosystem is a fab. Today, India does not have a fab of its own, and still needs to depend upon Chinese or Taiwanese or European or American fabs to be able to manufacture their chips. So manufacturing is still a missing piece in the entire puzzle, but I think we have pretty much all the skill set to dominate the sector in India. What do we as a student basically focus on to acquire a good knowledge for future references? Good question. I think the key two things you need to stick to are your basics, right? Now, I still remember my 4-hour-long Wipro VLSI interview where they grilled me for 4 hours. He even started offering me water and biscuits after 1 or 2 hours, thinking that I was extremely tired and exhausted. But it's a grueling session of questions that you would essentially go through to get into semiconductor space. But trust me, at the end of it, it's worth it. What you need to focus on are your fundamentals. And the entire 4-hour interview that I had, in fact, I even remember taking a book on VLSI manufacturing along with me. It was in my armpit, and I went to the campus placement. It was in Munnar Engineering College at that time. I didn't even have to open that book. Right? The stuff I read from that book were not even pertinent. They were asking me basic stuff such as digital circuit design, electronic circuit design. So chip design is all about two fundamental things. It's mainly about digital circuit theory or digital circuit design or analog circuit theory. And if you are strong in these two fundamentals, I think you have nothing to worry about. And I think you've got a great set of faculty at University College of Engineering to impart that education to you. You could also maybe do a lot of reading up about, the latest and greatest. I think I see a lot of great questions coming in from you guys. You just continue reading more and more about the industry. And, there's a lot of stuff that they could even ask you from there. But I don't think you need to really bother about, the latest and greatest in the industry, because that's something you will anyway learn when you're in the industry. I would say stick to your basics. That's what is the most important, not just for electronics, but for any branch for that matter. That's where you start your career, right? They're not going to expect you to be able to become an expert VHDL or Verilog coder. They're not going to expect you to be an expert user of ICC2 for place and route. They're not going to expect you to be an expert at static timing analysis. You probably don't even know what setup and hold is, right? What setup and hold are. So focus on your basics, because the ideology here is, or the basis for selecting a candidate is how good are you with your fundamentals? How well could you handle a small task? Or rather a relatively smaller task in your engineering college degree, which would enable you to handle a bigger task in the semiconductor industry, because you take on responsibility when you get into the semiconductor industry. So focus on your basics is what I would recommend you to do at this stage. Which do you prefer, Intel or AMD? I would say both, my friend, because both of them are my customers, and both of them use my technology to build their chips. I think every company essentially has its own secret sauce, has its own sweet spot. Some of the companies focus more on CPUs, some of them focus more on FPGAs, some of them focus more on GPUs, Some of them have even Intel. You mentioned Intel. Intel has a has a dedicated business unit to focus on artificial intelligence chips. How quickly do you access the RAM, ROM, the cache, the L1, L2 cache? How quickly do you do the memory access? How quickly does the bus operate? How efficiently does the interface, the interaction between the processor, the memory, the bus, and the peripherals essentially happen? A lot of things are happening in that area. So I would say don't go with a particular logo. Just follow your heart, and that's what would be important.
That's a tricky question too.
Sorry?
That's a tricky question too. Intel or AMD.
Yes. Would you please explain about quantum supremacy? Okay. So quantum computing, as I mentioned, is definitely something interesting. It gets deep into the root of how matter behaves, right? How quantum physics operates. How the energies in the different bands of the electron orbits around an atom, around a nucleus, are essentially structured. I would say it's tremendously high, but given the fact that there are a lot of considerations that have to be made in view of quantum computing, I'm not too sure about the scalability of the technology. Right? So today, if you have a quantum computer, you have to even be worried about a truck going by outside, because the overall electronics is so sensitive to even that kind of a vibration or electrostatic discharge or electromagnetic induction. You would have to completely isolate it. So thinking about something like a quantum computing processor getting into something as tiny as an ultrabook or even a PC for that matter, I would say is in the distant future. But it's definitely an interesting technology, and I would suggest, Jobin, that you go to IBM's quantum computing website and try it out for yourself. Just see how quickly, how effective quantum computing is for yourself.
Thank you, Jobin. And next question is, next chip design hub in India from Lija Jones.
Okay, so Lija, the next chip design hub in India. Interesting question. I presume what you meant by that is where is the next chip design concentration of chip design going to happen in India, right? So I think in India today, as of now, the largest centers for chip design are predominantly Bangalore, Hyderabad, and Pune, in that order. Purely given the fact that the number of companies that are established there are, pretty much in that order, and the number of semiconductor industries are there. I'd say the largest is Bangalore, and it will continue to be Bangalore for a long time, because many of the big semiconductor companies have their primary stakeholders or the primary P&L holders in Bangalore, right, as far as India is concerned. So I would say it will continue to be Bangalore for a while, but of course you have Noida and Delhi, right, where you also have companies like NXP, and a couple of other companies who are essentially established there. So I'd say predominantly Bangalore as of now. Okay, Solomon, Samsung uses two different chipsets according to the region we are in. For example, if we consider what are the latest flagship, even if the price is identical in all regions, why the China's chip is more power hungry and a bit in the Snapdragon? Is it like we are paying for the same device and getting an inferior one in India? No, so I think again, just to help you how we build an electronic system, right? There is a parameter called BOM, or bill of materials, and this BOM would essentially be the total aggregate cost of all of the chips, the cost of doing any custom manufacturing if it's there, the cost of PCB manufacturing and validation if it's there, and the cost of integration plus the software, everything put together, right? Plus, of course, the mechanical packaging. So that would be a BOM cost. On top of that, you add your margins and you would get to something called the COGS, or the cost of goods sold. Now, every company has its margin between the BOM or the COGS. That is not, there again, the BOM would also have a loading of the local taxes, the import duties and restrictions that you may have, and the loaded cost of having that particular product shipped to India. So while in certain cases the chip may come to India or and may be built in India or developed in India, the chip may end up becoming cheaper or will be available to you at a lower price. A classic case is the iPhone XR, right? iPhone XR was a made in India device, something that we're all happy about. So what happened there is they brought the different parts to India and they assembled it in India and they did the rollout from India. So by virtue of that, what happened is the price of the iPhone XR was a much more reasonable value. Was at a much more reasonable level. Now, if you've noticed the way Apple used to roll out its devices, right? Initially, they had a huge import duty for their devices. Now they've, I think, collaborated with India and have essentially negotiated on the import duties and what it's going to cost for the prices for the devices to be shipped into India, with some of the manufacturing happening in India. And because of that kind of a government-to-government transaction which has happened, there is, I'd say an inequality in the prices between what you would see in the United States. The last time when I went to the US, I was trying to buy, a pair of AirPods. And what I noticed is that the price there is pretty much the same as what it is in India. There's no price difference. Similar is the case of the phones or the Apple Watches, right? So the price difference is coming. It's not exactly the same. But it's coming lower and lower for many of the electronics. And I think to answer your question, the processor that they use inside it, what they would essentially have tried to do, and I'm just guessing. I'm not the one who architected the PCB, and I'm not sure of how the basis behind this. But I'm guessing that the overall feature set that is delivered to a customer may not necessarily be affected by this. And it may be that one of the chips that they have used is different in the India manufactured case, but it may not necessarily be that it's inferior, right? Which is the reason why they have a global warranty. I'm not too sure about if Samsung has it, but I know that Apple devices have it. You would have a global warranty for many of the devices. It doesn't matter where you procure it from, it would have a global warranty. So you could just take it and get it serviced. It doesn't necessarily mean that it's inferior, right? It doesn't necessarily mean that it's inferior. It may have concerns of maybe being more power hungry or not. But then this is again something that you would essentially, as a consumer, have a choice to make a trade-off on and decide which device you want to pick. Because their justification would be, hey, this is what we can afford for this particular price point in India, and this is the best we can do. So I think they're just trying to balance out the BOM cost with the COGS in order to be able to make the product affordable in India, at the same time reach the same feature set without compromising on any of the quality parameters. I'm not too sure about the power consumption, but at the same time, be able to give you a warranty so that the device works effectively.
Sir, but in India, we don't have an option to choose between Snapdragon and Exynos devices. We only have a choice of Exynos. If you choose a Samsung device, we only have the option to choose an Exynos device. So, if we consider both the Snapdragon X65 and this Exynos chipset, I think Exynos is a bit behind the Snapdragon X65. I think so. It has a 5G modem in it, and it overrides the Exynos device. So, by only providing the Exynos version in India, what will be the business strategy behind this?
Yeah, I understand what you're saying, Solomon, but what I'm trying to tell you is that the Snapdragon may be a little bit more expensive than the Exynos, which is why when Samsung wanted to launch that particular device in India, maybe they could not afford to have a Snapdragon processor in it, right? And still reach that price point, because India is a very price-sensitive market. So they would probably have done this. If you remember the slide wherein I showed you the entire cycle of user to design cycle to come down. When they define what the user wants, they also define whether the user will buy. Because if I price my S20 today at let's say 10,000 rupees more than what it is in the market abroad, you would definitely not buy it. You'll say, why the hell should I buy this? I'll go for an iPhone, right? So there is a sweet spot to pricing a particular device for a particular market. And if you exceed that, they know that they will not be able to sell enough volumes to amortize their cost and be able to be still affordable in their production line. The product would fail in that particular market. So what they would do is they would maybe flip out a part or two and be able to essentially give you the same feature set. Maybe it would consume more power, but essentially it would give you the same functionality as the one that you get abroad. But then again, the choice is yours as a user, whether you really want to go with procuring a device from India, which has an Exynos processor, or a Snapdragon processor. But the simple reason behind this, I'm guessing, again, as I mentioned, I'm not too sure about this, but I'm guessing, logically speaking, the reason behind it could probably be because they were not able to meet the expected price point, the ASP, or the actual selling price, as far as India market or the targeted user segment is concerned, with the Qualcomm Snapdragon processor. Right. So in a nutshell, Snapdragon is more expensive than Exynos, which is why they were not able to afford to bring it into the price point in India, because India would probably be loaded with other things like import duty and GST, which would bring the price up higher than their expected one, which may not necessarily be the case. For example, tax in the US is only 8%. Right. So for those reasons, that difference of 18% to 10% would essentially, to 8%, the difference of 10% would have to be compensated somewhere. So they would have to bring the price to a point of equality in such a way that the consumers in India don't feel exploited for doing so. Right? That's the reason why I brought out Apple as an example. Right? Initially, the devices were more expensive in India. Why? Because the import duty was extremely high, and hence the prices when it came to India in the market would be extremely high. This is not because they have a different processor. They have exactly the same processor. They have exactly the same co-processor. They have the same GPU, the same kind of display. But essentially, because of the loading of the local administration in the form of taxes and import duties and stuff like that, the price would go high. But the Apple consumer base is different. I hope you.
Sir, can I ask a question?
Yeah, go ahead.
So when a company like Samsung launches its top-level flagship phone with a price tag of almost 1 lakh rupees, it would surely target the richest people in India, right? So why would they cut off the price? They are targeting the richest people in India.
Yes, that is true. That is true. But again, probably when you get into the industry, you will understand that the sensitivity in what
buy the devices at a high price.
Solomon, the last part of your question got broken. Can you just repeat that again? Solomon, I didn't get that question. Can you just repeat yourself, please? This is just the last part.
So why would they prefer to cut off the price for a chipset when they are targeting a high class of people? The company target to cut off the price in their chipset when they are targeting a high class of people.
Yeah, again, see, Solomon, when you say high class, right, that's a very relative term. So I may have an iPhone 10 today, and I may have bought it for 1 lakh rupees. But I will definitely not be prepared to buy it at 1.2 lakhs, for example, right? If the price would be so in India, if I could rather ask one of my friends who's in the US to bring it down to India. So the problem with that is somebody who's price sensitive may be concerned about, let's say, a 20% higher price in India. Some of them may not be. But what the company does is they would do the overall analysis of the entire set of demographies and say, okay, maybe some of the super rich guys, who don't really care about $20,000 may just buy it. But there may be people who just love technology and who want to buy a phone and would say, hey, why should I spend 20,000 rupees more when I might as well just go for an iPhone 11 Pro Max or 11 Pro, whatever, right? For that same price point. So there are a lot of factors which essentially add to it, and this is not just making a blanket statement saying it's targeting only the rich people. Would not be taking into account other parameters such as the users who would stretch to buy a phone, for example. Some people I know even take a loan to buy a fancy phone, right? So they'll be losing those users. They would be losing users, for example, who don't have somebody in the US who would necessarily bring them an S20 shipped in from the United States. They would be losing users who would be looking at a benchmark of India price versus US price and say, hey, I don't want to buy something. I don't want to be 20,000 rupees extra just because I'm in a different country. Right? So taking into account all these parameters, that's probably why. Again, a word of caution here is I don't know because I'm not a part of the Samsung team that built the phone. But purely from a logic standpoint, I'm thinking that this flip in something as crucial as the key application processor was done purely because they had to meet a particular price point. So the actual selling price of the ASP that is defined in the market has a lot of parameters that they take into consideration, and it may seem like just a $5 or $6 part, but when it goes into production and comes out, the net I would say BOM, COGS, ASP, it goes up. It's not a linear fashion because the loading goes up in a compounded way and the price goes up exponentially, which is why, even in the automotive segment, right, you would notice that many of the cars use cheaper plastics. You say, hey man, how much is it going to cost you to use a little bit better plastic here? But every rupee that they spend on a car is going to have an impact on the number of sales that they make. Similar is the case with even the S20, I'm guessing, because even a rupee difference would essentially bring an impact to their user base in India. Does that answer your question, Solomon?
Yes, sir.
All right. How was your journey from an employee to director of Wipro Japan? Okay, interesting question, President. Thanks for that. Yeah, so I, as I mentioned, I started off as a chip designer with Wipro, building chips for companies like TI, Intel, and Qualcomm as a consultant in DFT, or design for testability. And what I used to do then is I used to specialize in something called programmable built-in cell test. And what this essentially does is I would build a collar around every memory in the design. It could be a RAM, a ROM, or EEPROM, or a flash. And essentially that memory would be tested using built-in cell test engine, which is controlled using something called a VLCT, or a very, very low-cost tester. Now, that essentially would be the key to what I was doing there. And then, of course, there are things like scan insertion, pattern generation. I was essentially an architect for the design for testability aspects of the chip. From there, I got kind of bored, and I discovered my passion in doing more of business transactions, and I got in touch with a couple of people and found out about what it's going to take for me to move there. And from there, I moved into a solution architect role, where I was essentially helping many of there were 3 or 4 of us as the key architects from Wipro who were doing the entire architecture management of all of the proposals that were being built by Wipro for their end customers. And from there, it was a very steep learning curve for me into being just a DFT engineer to knowing all about silicon design. From there, I think throughout my career at Wipro, I've done close to 9 different roles. Although I spent only 9.5 years at Wipro, I did 9 different roles at Wipro. From there, I moved into a business head responsibility for India and ASEAN. I spent around 3.5 years as a solution architect, around 3.5 years as a chip designer, and then the remaining soon after those 7 years, I moved into a business manager role for India and ASEAN. ASEAN would be the Association of Southeast Asian Nations, which would include Singapore, Malaysia, Thailand, Philippines kind of countries, and all these. And then finally, from there, my next year was in Japan, Yokohama in Japan, where I was managing Japan, the semiconductor business, and also all of the territories in product engineering, including Korea, China, Taiwan as well. Yeah, that was what my journey looked like. Okay, Francis, that's an interesting question. Why Intel failed to deliver their 7nm product recently? Yeah, that's a great question. So I think there's no single answer to what went wrong with Intel. In fact, I was recently reading an article about how other companies such as NVIDIA and AMD have passed on from Intel as being the largest semiconductor company, and how Intel has gone through a lot of hiccups. So there were a lot of changes at the top level management at Intel. And I think the reason why a particular chip is not able to make it to an industry in time has different aspects to it, right? Has different reasons behind why this necessarily doesn't happen. But I think in Intel's case, what essentially happened is they had a lot of failures in their timing analysis, in their placement route run, physical verification runs, and they were unable to get the product to market in time. And the problem with a chip when it doesn't come to the market in time is that it fails, right? Because your competition devices from AMD and NVIDIA or Qualcomm, whoever it may be, would have raced ahead of you in the market. And 7 nanometers is not a new technology, right? It's quite an old technology now. We're already at 3 nanometers now. So, I think when your product doesn't reach the market in time, when your time to market is exceeding the prerequisite to become a successful device, you lose the basis of your customers who are going to buy the chip from you. And when that happens, you lose out in the entire game. Right? So I think that's essentially what happened to Intel. It had nothing to do with the 7 nanometer technology, no challenges per se. I think it was just a combination of many things put together that led to their first design hitting the market too late for it to be relevant anymore or rather to have enough relevance in the industry to make it really big. All right, I think that's the last question we had for today. If there are any further questions, I would request you to email me. I'd be glad to respond to you. But Deepu sir, if there are no other questions, I think we can move to the next step. Yep.
Yes, sir, that was the last question, I think.
Okay, great. All right, thanks so much everyone once again for logging in, for taking time out on your precious Saturday evenings. Once again, good luck to all of you, and I look forward to meeting all of you at some point in time in the industry. Yeah, thank you.
It was very, really nice of you to give such a precious time to us. So we are very much thankful to you. Thank you very much.
Pleasure is mine.
Thank you all and all present here.
Thanks so much. You have a good evening.
And we will conduct more webinar in series. So all participants, please join for the next sessions. And we hope Robin sir also will be on this group for much more presentations further.
Most certainly. Most certainly. Glad to be.
Thank you. Thank you very much. Thank you one and all. I hope all of you have filled feedback forms and you will get your certificates by Monday. And hope it was an informative session, and hope you all enjoyed it. And let's have more sessions further. Thank you all once again. And let me remind you one thing. There are a lot of people behind this webinar where the names are not mentioned. I would like to mention those names also. Our HOD Ashaladam is Rajesh sir, Anish sir, Ansar sir, Ranjit sir, Amjada Miss, Asha Jayaprakash Miss, Krishna Priya Miss, and all in our department. So I would like to extend our thanks to all of them for conducting this webinar successfully. Thank you, Robin sir, again. Thank you, Principal, and thanks to our Director. Thanks to our Administrative Officer, Shivaprasad Katta sir, Vice Principal Jose sir. Thank you very much, and have you all a good day. Thank you.
Thanks so much. Have a good weekend. Cheers. Bye.